thing I need.
I can show you. Oh. It says this is MPX code. You cannot run it. I'm running it on top of this.
Partner and I finished it except for the fucking graph and lots of I don't know how to do this.
Yeah, okay. The part is good.
Can you finish it?
Yeah.
Huh? Yeah, I looked at it. I read it. Wow. That's a nice intro. What? That's a nice intro. Oh, thank you. And you know, like we played clocks before the lecture, right? And for some of you who is probably the first year in the United States, one thing you probably don't get used to is that you get 1 more hour sleep the weekend, the past weekend. But you know, like no pain, no gain, because in spring you are going to return it back. But the thing is that you will feel like your life is largely controlled by clocks. So for example, how do you know that you are here? You need to be here for the lecture. How do you know that I'm always here? Because you have the clock and you know when the clock time arrives, when it's 9:30, the lecture is going to be here. What do you want to share?
Wait, so doesn't that mean our lives are just controlled by clocks?
Well, I mean there are part of it. Well, you know.
And also the programs that we make are also controlled by clocks.
Yeah, so you got it. That's why we play clocks before, right? Because one thing you learned in the last lecture is that you learned pipelining, right? And there are many stages in the process pipeline. How each pipeline stage knows that I'm done with my work and is ready to receive inputs and generate output is all controlled by the clock, right? So see, we play a song for the purpose. Right, so whenever the clock signal arrives, it will trigger those pipeline registers to release its data to the rest of the circuits that it connects to. So for example, for the first stage, for example, like the instruction fetch, you can consider that the clock is probably controlled by control your instruction fetch unit, or say the instruction memory, which allow your instruction memory to output new data in the beginning of the clock cycle. And then at the end of the clock cycle, your instruction will be fed into the pipeline register, so that when the next clock cycle arrives, the red instruction showing previously can advance to the next stage. For example, instruction decode for the rest of the stuff. In the meantime, the previous stage can be yelled to other instructions. So that's the basic idea of pipelining. And the good thing about pipelining is that if you have sufficient amount of instructions, and if these instructions can continuous execution without any issues, then the ideal CPI after your pipeline is saturated is actually equal to 1, meaning that every cycle you are fetching a new instruction and generating outcome for a new instruction. However, in reality, that's never your life. Right? Like you learned in algorithm, you saw that your algorithm is going to grow in order n squared, but actually its execution time grows exponentially, because that's not the real world. So in fact, in pipelining, there is also 3 main issues we have to address, which is pipeline hazard. So we have 3 different types of pipeline hazard. We already talked the first one, structural hazard, meaning that it's because of your pipeline design doesn't allow multiple stages to execute without any issues simultaneously, largely because you have shared hardware resources that different pipeline stages may need to use. So the best way to address it is definitely you should revise your hardware design to make that not happening so often. Of course, there are still cases that you cannot completely avoid that, because whenever you modify the hardware, it also means that you are going to increase your cost, and people are always thinking about how can I save the cost, right? So sometimes you have the structural hazard. It's probably not because of the designer's fault. It's just a series of trade-offs, and then turns out that we have to make the hardware in this way. So if you have the hardware made in this way, then stall is probably the way how to address it. But as you can imagine, the performance is not as great as you would want. And another type of hazard that we are going to discuss intensively today is control hazard. It's the situation when we cannot 100% for sure what's the next instruction to execute. The last one is data hazard, meaning that an instruction is depending on the output of a previous instruction, which we will talk about later in this week. So first of all, one thing, right? Like in the last lecture, you probably learned that it's really important if you want to know if there is a hazard, if there is a situation that will cause incorrect execution outcome. One important technique skill you need to have, which you should brought from your undergrad computer architecture, is the tips of drawing a pipeline diagram. So in RISC-V, for example, we will have 5 pipeline stages. And as we mentioned, to avoid a structural hazard, we force every instruction to go through all 5 stages. So if you see there is one instruction having 4 stages, you have something wrong, right? And another thing is that because you also want to avoid a pipeline hazard, so if you draw a pipeline diagram and it turns out that it shows that you have 2 instructions in the same stage, that's also not correct. And another thing to think about is that how do I know if the instruction is entered to leave the current stage? The answer is this, right? No other instruction is using your next stage first, right? That's how you can enter, right? And the other thing is that the instruction has done its own work at this stage. And finally, I'm ready to go to the next stage in a way that I have all inputs that is necessary available. And I can only fetch a new instruction if I know where is the next PC to fetch, or we can predict the next PC. and flush an instruction if a branch resolution saying that is predicted. So today we are going to talk about this part. All right. So last week we also talked about the impact of control hazard, right? So if you don't know what's the next instruction to fetch, then in an optimized risk five-stage pipeline, it will cause 40% increase in CPI. Even with an optimized one, you still need 20% increase in CPI because the optimization actually just move the branch outcome a stage earlier. Before that, you still have no idea what's the right instruction to execute. And so this is a huge impact. So to mitigate this input, today we are going to talk as many as possible regarding this branch prediction methodologies, and hopefully we will show you some interesting example how branch affects your coding. All right, so last week we talked about the reason why we do not know what's the next instruction to fetch is because first, if the branch is taken, we have no idea what's the target address. And the second thing is that we don't know if it's taken or not, right? So how do we address that? So first of all, if you pay attention to the branch target address, you will figure out that the branch target address is always calculated as PC, which is the current branch instruction that is in the compiled order. So if it's compiled, it means that it's static. So your branch PC for an instruction would never change, even though this branch instruction will be executed multiple times, but the PC of that instruction is always the same. Plus an offset, which means that how many instructions from the current PC is where you are jumping to. So if the PC is fixed, and this is also fixed, the branch target address for each compiled instruction is in fact a fixed number, or say a constant. So in this way, how can you you can address this by creating a cheat sheet, hardware cheat sheet. Whenever you process a branch instruction, you also record its target address. So the next time you don't have to compute it. Instead, you just see if I have recorded its target address previously. Okay, so yes?
For the third option, don't you mean result of ALU is out?
Not out. Cannot. Okay, is out. Yes. Okay, right. And okay, so for the first statement, right, you need a branch target buffer to address it. And for the third statement, that's actually more problematic because we don't know if this branch is taken or not, right? So the best we can do is guess, right? So today we are going to talk about how do we guess. So first of all, right, given that if we want to do branch prediction, we need a cheat sheet. So here is a very basic dynamic branch predictor. So in this dynamic branch predictor, first of all, these are the items that are already in your processor. You need a PC, and it always PC plus 4 if it's straightforward instructions, right? And now, as we said, you need a cheat sheet. So we add this thing called branch target buffer, and this is just a reference design of the branch target buffer. And most of the time, well, in a lot of cases, we probably won't record a branch PC. We just use an index, and sometimes it's just your branch PC might not even be correct in this case. But this is just give you an idea what a branch target buffer looks like. So basically, there is an index or there is something help you to see if the instruction that you are fetching is a branch or not. And if it's a branch, and you can see if there is a target BC recorded. And the other thing is the state. This state is actually a very short history regarding what happened to this particular branch in the previous 2 runs. So how are we going to deal with this state? So the first thing is that, okay, so if, so for this example, right, if we are right now fetching the branch instruction 4080, and wow, it's in a branch target buffer, right? So we know it's a branch for sure, and we know it's target PC. And we look at the state, assuming 1 tells you that we are going to predict the branch taken, then what would happen is that instead of using PC plus 4, we would use the target PC as the input for the next instruction fetch stage. So in this way, it means that you can predict taken, and when you predict taken, you can also fetch instruction for the target address, and then the rest. But when you finish executing this branch, we also take the feedback from the ALU, which tells you what the actual outcome of this branch to keep updating the state of this branch target buffer. All right, so this is a very basic concept. So this kind of branch predictor is called 2-bit bimodal local predictor. So there are a few terms here. So first of all, it says 2-bit, meaning that we use 2 bits to track the state of each branch. And it's called local predictor because we have states associated with each branch instruction local. And there is definitely a global predictor we will talk about later, but right now just remember the concept of local means that for each branch, it will have its own states trained separately. And whenever you produce an outcome of the branch instruction, this state will be changed. And if we guess it right, remember what happened in the pipeline, right? If we guess it right, there will be no delay. If we guess wrong, right, all you need to do is to flush the incorrectly fetched instruction, and then it's just 2 cycles wasted, which is equivalent to the time that as you do nothing, right? So it's definitely no harm in this way comparing against without any branch prediction. So it's nothing to lose. That's what I would say about branch prediction. So okay, now regarding the states, as I said, the states represent the last 2 runs of the branch. So if the last 2 times we run this branch, it says that it's not taken, right? We put it 0, 0 here. So since the last 2 times are not taken, why should we predict taken, right? So that's the basic idea. Okay, and if it's 0, 1 means that the last time is taken, but 2 times ago it's not taken. So, let me stay back a little bit. Maybe observe one more time, right? So that's the philosophy of this. All right. So if it takens again, right? So if you have the incremental counter, right, saying that it goes to 2, meaning that the last 2 times they are all taken, then I am confident that okay, since the previous 2 times are taken, we can definitely we should definitely predict it taken. And finally, it's saturated right at 3. So if the last 3 times are all taken, okay, so I think I got it wrong. So the history actually is allowed to track like 0 to 3, right? So it's actually an incremental counter, right? So if the last 3 times are all taken, we will go to the strong taken stage, meaning that you are right now in a very confident stage that, well, it must be taken. Right? That's how you guess. All right, so this is the state machine. So it's basically an incremental counter. So once you are in a strong taken stage and you figure out that, well, this time it's not taken, you will decrement your counter to 2, right? Which means that in the previous 3 runs, there are only 2 times taken. And if it decrement to 1, then I'm less confident, then I will predict not taken. So this is the statutory count, how they use this 2-bit as a statutory counter that goes from 0 to 3. And once you have taken, increment the value by 1. Once you not taken, decrement the value by 1. And if it's above a threshold, greater or equal to 2, it predict taken. So that's the basic idea of this one, right? So with this one, let's go through this example. So for this example, the only branch is here, plus plus I equal to, smaller than 10. And if it's smaller than 10, meaning that we are going back to the loop. So this means that, okay, so here, what's the definition of taken and not taken? If you are going to the next line, that's not taken. If you're going other direction, that's taken. Okay? So in this case, if we are going back to the loop, that's taken. So when I equal to 0, should it be taken or not taken?
Not taken.
Taken, right? All right, so here we go. So let's go through this. So let's say like when I equal to 1, and when we say that, well, we initialize the state to be 1, 0. It's a little bit cheating here, but let's say let's start with 1, 0, right? So you know it's taken, and if it's 1, 0, it means the value is 2, right? So we predict it taken, and the actual outcome is taken, right? So what's the new state in when we look at the branch when I equal to 2? It's going to be strong, right? So when I equal to 2, it will move to strong taken, right? And then predict taken, the actual outcome will be, okay, how many times this situation is going to repeat? Well, until we reach 10, right? So what happened at 10? We are still going to predict taken, right? Because all previous branches are taken. However, is it taken or not? Not taken, right? So for this 2-bit local predictor for this pieces of code, you can assume it's 90% accuracy. And the reason why I put the initial state to be 1, 0 here is because if we thinking about it, this is a frequently called function, right? And if you run this for the second time, because when you have I equal to 10, your state will be 1, 0. So that's why I'm saying that it's possible. If this is not a first run, you can assume that the state is 1, 0. Yes.
So on a default machine, is there a program where like for this prediction, okay, if the first one's taken, it's set to 0, and if it's not taken, it's set to like a weak taken to 1.
You are saying that are we going to set the initial condition differently based on the first one, or?
Yeah.
Typically, no, right? Thinking about that, what you do in the very beginning is that you just zero out everything. But when you run a new program, it's very likely that there are some side effects left over. And we typically don't claim that. So it's typically like a random value. Yeah. All right. Okay, so in this example, right, 90% of accuracy. And with this 90% of the accuracy, you can consider only 10% of the time you need to pay the 2% two cycle penalty. So your CPI is now significantly bring down to 1.04, only 4% of the penalty. Right? Good deal, right? So now let's look at this pieces of a code and see how 2-bit local predictor can do for you.
Where did the 20% come from in the last slide?
20% of the branch instructions.
Oh, okay.
up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Done. Okay. So this is what do you guys think? So there are still quite some. Well, there are still quite a few deviation on the results. So why don't you go ahead and discuss with your friend for another 90 seconds? Maybe you will find out a lot of you didn't get it right.
E because the branch X is taken 50% of the time, and branch X is taken approximately 100% of the time. So the average of 50 and 100 is 75. Yeah, but if we do it 100 times, so it's just but that's what I think of there.
All right, let's wrap up in 15
Wait, do they
seconds.
share the same math? Wait, what if they share the same?
5, 4, 3, 2, 1. Time is up. Okay, so after the discussion, more of you think it's E. So let's see. What do you guys? How do you guys change your mind? We want to share.
Does branch X and branch Y, is that the same counter, so it switches?
What do you think?
I assume that they were separate, but my answer
Right, but
was
why
C.
do you assume it's a separate?
I don't, because it'd be easier that way.
It's easier that way, but the biggest hint is actually in the name, right? 2-bit local. Local means that we have a state for each different PC,
Okay.
right? So does that?
Yeah, that answers that.
Okay, so if that's the case, how do you address that?
So, okay, so branch X is taken approximately 50% of the time.
Okay, how do you know?
Because it checks whether I is even or odd, and it's 50.
Right, so, and it only goes in one state, right? So this one, it predicts terribly, right? And, well, actually not that terrible, right? 50%, it's okay, right? And how about this one?
Branch Y, it's approximately 100%.
Okay, right? So here's the thing, right? So the second one is about 100%, the first one is 50%, and these two, the execution, the instances will be executed is equally, amount equally. So it's actually, well, another thing is that you can faithfully go through this one, and you can also find that for branch X is only 50%, and for branch Y is almost correct. So it turns out it's 75. Okay, so this example is simple, right? But are you satisfied? You're satisfied. Okay, so then I'll put 75 as your final score in this class. Is that okay for you? You don't want 100?
That's an improvement from my midterm.
Oh, that's an improvement from your midterm. All right. Okay. Okay, so if you are okay with 75, then you can take a nap. If you are not okay with 75, let's see what can we do better. And that's actually coming from a paper that you read called two-label global predictor. So you see the word global, right? What's global going to be different from local? So previously we said that, well, two-bit local predictor didn't do a good job. So the idea of global is that, is there a thing that we can do a better job? And what it identifies is that some brilliant figure out that, if you look at the actual outcome, ignoring which branches is it coming from, it actually shows there is a perfect pattern here, right? It's always 3 taken followed by following 1 not taken, right? So if we can predict the branch outcome by using this pattern that we identify, we can potentially getting 100%, right? So here's the thing, right? When you, I don't know how many of you have this experience, but like multiple choice questions, you can guess an answer based on how many times the professor likes C, or you can sometimes find, CAB, CAB. I saw the pattern. So the next part, what must be CAB? Or another thing you can think about is that I have so many C's in my answer, right? So the next one shouldn't be C anyway, right? So we should guess like B or something else, right? So those are examples of global predictors. Yeah.
Why the state of the third x is 0, 0?
Which one?
The third x.
Number 2.
Yep.
Zero. Well, because okay, so if you look at the x here, initially it's 0, 0. Predict the actual outcome is taken. This one gets incremented, but this one is not taken, so it gets decremented. Okay, so now there is a global pattern you can observe, and in real life, right? When you do multiple choice questions, you sometimes use the global pattern to predict. So it's not completely a surprise that a branch predictor can also use this kind of global history. So let me tell you how they use the global history in that purpose. So the idea of the global history predictor is a little bit different from the local predictor, is that we do not maintain the states per branch anymore. Instead, we still have the branch target buffer so that we know what's the target address to jump whenever the branch is taken. However, when we collect states, we just put one global history register here. So this global history register just tells you what's the outcome of the last 4 branches if you have 4 bits. So if you have a 10-bit global history register, you are able to track the outcome of the last 10 branches, regardless which outcome is from which branch. So that's the idea of global history predictor. So with this global history predictor, so for example here, 0, 1, 0, 0 means not taken, taken, not taken, not taken, right? So, and for each history, we train their states separate. So now, the global history register is different from a local in a way that the local predictor, it trains the states per branch. However, the global predictor trains the states per history pattern. So what does that mean is that, okay, if I saw 0, 1, 0, 0, what's the equivalent value of 0, 1, 0, 0?
8, 4.
4, right? So I'm going to 0, 1, 2, 3, 4, the 4th entry of the branch states. And it will tell you that, okay, next time if you see 0, 1, 0, 0, right, here's the state, 1, 0, right? And we can use the same counter definition as we used before. So we can say, well, when you see this, you predict it taken. Right? So that's the idea of the global predictor. So for this example, I still use the branch target buffer to get a target PC, but in the meantime, I can use the global history register to see its outcome and predict taken or not. So whenever it's predict taken, I just use the target PC to fetch the next instruction. And again, the LU will provide feedback of the actual outcome of this pattern. Okay, so let's walk through the example that you just practiced. So for the global predictor, right? So for this piece of code, when I equal to 0, right? What's the branch outcome? Not taken. I equal to 0, right? Not taken. Okay. So for branch X, not taken, and currently there's nothing here, right? So the history was like 0, 0. And here I only assume that I have 3-bit history. Okay, and now, so this state is 0, 0, predict not taken, but the actual, oh, it's actually taken, man. So when I not equal to 0, right, you are going to the next line. And if it's equal to 0, you are predicting taken. Okay, so it's actually taken. Now,
So we say a branch is taken is to say the PC jumps forward.
yeah, jump forward or backward. Whenever you are not going to the next statement, it's taken. Okay? So after doing this, right, then when I run this branch y, the I value will be incremented by 1. But as you know, this is branch y, right? So this is definitely taken, right? In the meantime, your GHR, because the last branch is taken, so it's actually updated as 0, 0, 1. But again, we never seen this pattern before, so the state will be 0, 0 for sure, right? So pretty not taken, and the actual outcome is taken. Now, when I equal to 1, when I go to branch x, yes?
Why is the actual like taken?
What?
Why is the actual
Because you're not going to this line. If you go to the next line, it's not taken. Taken means that you are going somewhere else other than your next line. Is that okay? Yeah, this is a little bit confusing, but that's actually the actual definition. All right, so now when I equal to 1 for the x, is this taken or not taken? This time it's not taken, right? But in the meantime, the GHR, what's the right GHR here? Okay, well, how do you update the GHR?
Or is it 0, 0, 1?
Shift and the previous outcome, right? So what's the right value here? 0, 1, 1. Okay, so it's actually 0, 1, 1. But have we seen this pattern before? No, so the state is 0, 0.
Wait, so we shift left.
You just, okay, so here is the quick thing. Just look at this column. What was the last 2? Last 3. Right? Okay, so now we are predict not taken because we haven't seen this pattern before. So for this one, is it taken or not taken? We said it's not taken, right? So as you can imagine, right, the next time your GHR will be 110, right? So when I go to the second run of the y, it will be 110. Again, we haven't seen this pattern before, so it's not taken, right? And the actual outcome is still taken. So now, when I go to x again, now I equal to 2. What's the GHR right now? 101, right? So have we seen 101 before? State 00, right? And so predict taken or not taken? Not taken, right? And is it the actual outcome taken or not taken? Taken, okay. Now, when I equal to 3, go to y, what's the current GHR? 011. Is the state taken or not taken? Okay, what's the state actually? Okay, so the last time we have 011 here, the state is 00, and the actual outcome is not taken, right? So what's the new state? 00 again, right? Because it's not taken, right? And it's a saturated counter, right? Predict taken or not taken? Not taken. So the actual outcome of this one is taken or not taken?
3 y, it is taken, right?
It is taken,
Because it's the
right?
y zone.
Right, it's y. So the next time when we see this 011, you can imagine it should be incremented to 01. Okay? So now, what's the current history? 111. Have we seen this pattern before? What's the state? 00 not taken. But for this x, is it taken or not taken? For x equal to 3, it's not taken, right? So when it's odd, it's not taken, right? Okay. So now, from now on, you will feel like, are you fooling me? How come is it doing anything better? Be patient. Be patient. Okay, let's keep going. When I equal to 4, what's the current GHR? 110. Huh, have we seen 110 somewhere before?
Yes.
Okay, so here, right? And here it was like taken. So this time it will be 0, 1, right? However, if it's 0, 1, are we predict taken or not taken? Not taken. What's the actual outcome for this? Taken, right? So, hey, something is changing here. Right? You can imagine the next time it will be 1, 0, right? So when we see the pattern next time, the outcome is going to change, right? Trust me, this one will be better. Okay, now I go to 4x. What's the current pattern? 101. Have we seen 101 somewhere?
Yeah.
Yes, right? Here. So what was it last time? It's
0, 0.
so now it should be 01, right? So you can also see this one may be changing, right? So although we predict not taken, the actual outcome is taken this time. So the next time it may be updated to 10, right? Now, why? What's the current pattern? 011. Have you seen 011 before? Yes, right? And well, again, we are saying taken or not taken. Not taken, right? So this time we are still getting it wrong, but the next time will be updated to 10, right? So it's going to be different. Now, this time, what's the current GHR? 111. Have we seen 111 before? So it's 0, right? Taken or not taken? Is it taken or not taken? Not taken still, right? Because it's odd. Okay, so now when I equal to 6, why? What's the current pattern? 110. Have we seen 110 somewhere?
Yeah.
Yeah, right? What's the new state? 10. Taken or not taken? Taken. Is it taken or not taken? Woohoo, we got it right. Right, finally. And now, for this one, what's the pattern? 101. What was the last stage?
Oh, wait, we'll get the taken.
We will get it taken, right? Then this time, well, the next time when you see this, they will be 1, 1. So if you keep going, like 0, 1, 1, we've seen this before, right? Is 1, 0, taken, taken, right? Now, for this one, 1, 1, 1. Hey, we have 1, 1, 1 here, right? And it's still 0, 0, not taken, and actually not taken, right? Now, this one, 1, 1, 0. You see 1, 1, 0 here. It predicts taken and actual taken, so it will be saturated here, right? Woohoo. So if you keep going, you will figure out that from now on, from now on, from now on and on, every time is correct. Did you see the magic? Everything becomes perfect after some point. So sometimes just be patient. Okay,
Why do you say you're perfect?
near perfect because this is not perfect, and near perfect means that you are still going to mispredict the last one, right? So nearly perfect is not perfect, it's never perfect, right? But thinking that if you can guess this percentage of correct, it's already good, right? All right. So now I'm asking you this question. We have two types of predictor for this 4 pieces of code. Which one is better?
It's taken if the if statement's true.
No, it's actually, well, it's taken if the statement is true. Depends, right? If it's taken if you are not executing the next line of code.
Wait, but by the next line, so like for suppose for 1, is the next line of code times equal 2 or is it plus equals I? Because like the indentation like makes it
Which one?
for number code 1.
Uh-huh.
So does that so is the next line of code times equals 2 or is it plus equals I?
What do you think?
I can see arguments for both.
No.
Is it
So for C programming language,
yeah.
right? If the condition is true, if I don't have a bracket, it always the next line is considered as the statement following if the condition is true.
Oh. So if the condition is true, then it goes directly to the next line in C.
If the condition is true, it goes to the next line. Yes. So in this case, it's not taken.
So if the statement is true, then it's not taken.
Well, don't judge that by that, because sometimes if it's true, you may go somewhere else.
Oh jeez.
Oh. All right, let's wrap up in 15 seconds.
I can't do that. You have to look at where it comes. Yeah, but how do you know?
All right, 5, 4, 3, 2, 1. Time is up. Okay, so let's look at what do you guys think? Uh-oh. Okay, definitely we need some discussion real quick. So why don't we have a discussion in 90 seconds?
So I predicted. Yeah, I predicted the first one. Oh yeah, you're right. Oh yeah. Yeah, it's a great tool. Yeah. I thought they would perform the same amount.
Just one.
So there's like 3 bits, right? Okay, that's
Okay, so so 5 is so shit.
All right, let's wrap up in 15 seconds.
He said it was awesome. That's modified. Yeah, but it's still brand.
5, 4, 3, 2, 1. Time is up. Okay, let's see what you guys think after discussion. Slightly changed, but whenever I saw you guys chose B, I know it's a local brand predictor, so that's why I want you guys to discuss. Right? So, can someone share with me your group discussion regarding which one outperforms? For global to outperform the other. Anyone want to share? Anyone want to share? Okay. Okay, so for the first one, why do you think the global is going to outperform? What kind of pattern?
So the
will like the local will have to
For the local one, right? This one you can have at most 90% of the actors.
Yeah.
Right? How about the global one?
the global one. Okay. The global one will probably
Okay, so for this 90% of the time, right? So there is one time that the global one will produce. Okay, so if this is so this is always so for this one it only taken once per 10 runs. Right? So you will see this is generating a lot of zeros most of the time, and this is always taken. So you can see most of the time you are seeing patterns like this, but once in a while you will see a pattern like 1 1.
Wait, isn't it not taken once every 10 runs?
Well, it's not taken most of the time.
Oh, sorry.
Yeah.
That.
Yeah, but the thing is that this chance is rare. So if you can only see this pattern. So you have to know that you repeated this for 9 times to know this one is not going to take. So for this one, I would actually say there's actually no difference between the two. Because the issue is that yes, the global history helps in this case, but we only have 4-bit global history. So it's not long enough to capture the whole thing.
Wait, but when it capture up to 16, what's the relationship between what we can predict and the global history?
So the thing is that you have to see the repeat pattern. Right? So for this case, right, you have 10 not taken or 1 taken branch.
Yeah.
Well, so 9 out of 1 out of 10. Right? So which means that you need to at least be able to capture this whole 9 things before the 10th happen.
Oh, so we need a 10-bit global history.
You need actually, I think, 18, right? Because you also have another branch here. So you need to see a pattern like 0, 1, 0, 1, 0, 1, 9 times to know the next one is 1, 0. Oh, 1, 1. You see that? Right? So then you need very long history to get it. Agree?
Yeah.
How about the second one?
oh the second one I think there's probably
Right, so the second one is about the same. How about the third?
the one the while
So then the global one will definitely get it right. But the local one is only doing 50%. So how about the last one?
that one because the inner branch so it doesn't really have pattern.
Right, so the other thing, right? If it's random, no one is not going to do well as well for the global in this branch. And another thing to think about is that because the random one, it create randomness for the global history, right? So actually it messed up the history a lot. So this is probably a better case that local is better because for the global history, right, you have some randomness there, right? So this is a case where local could be better because local, it has its own history, will not be affected by the randomness, right? So actually the answer is B. See, the majority is not always. Okay, so now since global and local has its own strengths and weakness, how can we combine their strengths but avoid their weakness? So that's actually what computer architects try to do by the end of the last century, which is called hybrid predictor. The first type of hybrid predictor is called G-share predictor. So the G-share predictor is still following the idea of global history register. However, as we said, like the case we said, there is a randomness. Whenever there is a randomness in your history, we don't want that to be messed up. And how do you filter out the situation you have randomness in the history? Is that their idea is that okay, instead of using the state directly, let's take a few bits from the branch target PC to concatenate your history. Right? So for some so it's actually a combination of your global history and your branch PC. So we combine these two inputs together to train the states separate. So in this way, you can think about, for some sense, for the second branch that we saw in the last case, it's actually have a meaning that this state is trained for this PC when I see this, right? So in this way, you can avoid some randomness in the global history without adding a lot of hardware costs. So in this way, right, as you can see, we don't actually have more tables. However, with this input, it somewhat avoid the randomness of the other branch, because when you look at a pattern, you always have this inputs. Okay, so yeah, so the G-share predictor actually allowing the predictor to identify both branch addresses, but also use the global history. Another one is called tournament predictor. So when we say tournament, right, you have the idea of competition. So the second one called tournament predictor is actually saying that I have two sets of predictor or even multiple sets of predictor. And above the predictor, I have a predictor. Sounds pretty awkward, right? So what's the meaning of predictor? So let's show this example. Again, the branch target buffer now have a state. But this state, instead of using a state to predict the branch outcome, this state just indicates for our history which predictor is more likely to generate the outcome is wrong. So let's say if you have two predictors that you can switch from one another, this state actually tell you 0 goes to this one, 1 goes to this one. And what happened is that, okay, if it goes to one of the predictors, so for example, one is the global, the other is the local, right? And what it will do is that if currently, so for example, if it's 1, then we probably go to local. If it's 0, we probably go to global. But in the meantime, when your actual outcome comes, the branch predictor, the predictor will look over the state that's trained for local and global to see which one gets it right. So if one of them gets it wrong, it has its own logic to decide what was the next prediction we should use. So that's the idea of predictor. Right? So what happened is you predict which predictor to use, right? And if your local predict, so the tournament idea is that, well, we just have two predictors, and it tells you which predictor would more likely to generate the outcome. All right? So this idea is simple, and I skip a lot of the details. If you really want to dig into the details, the textbook has a lot, but since this is the computer science class and you guys are not going to implement this predictor by yourself, and whenever you need to implement a predictor by yourself, there are tons of materials you can reference from. So I'm not too enthusiastic about telling you what exactly how we do it, but just give you a concept, predictor. All right. Now, another type of predictor is actually one of the very frequently used ones right now. It's the Tate predictor. So remember this one, right? And we mentioned that global predictor can work well if the history is long enough. But there are also cases that you don't want that many history to be used. And in fact, if your history is too long, as some of you might already experience, it takes a long time to train the predictor, right? So the LTAGE idea is that I have many different labels of predictors that you can choose from. I have a very long global history register. However, for each branch, I have a decision regarding how many bits of history that I should use to predict the outcome. So for some branch, I do record that. So here is the state, right? It tells you like how. So for example, if I have 8 different sites of the history that I can look for, this state will actually tells you for now what's the length of the history I should use to predict the branch outcome, right? So it's actually a combination. Again, it's similar to the idea of predictor, but it's actually predicting which global predictor I should use to predict the current branch. So for tournament, is combining local and global, but for LTAGE, is combining global predictors with different lenses. All right. Now, the last one, which you might feel more exciting about, is perceptron predictor. It's actually, and the thing is that you will be surprised how early this paper is published. Well, 2001. So a lot of you think about, well, this neural network is something new, but actually, if you go to the history, you will figure out neural networks was once very hot by the end of 20th century, and then because of the limitation of computation, people figure out it's not a computational feasible idea. So that's why it gets cooled down. But later on, because we have a lot of hardware accelerators like the GPU, allowing neural networks to be compute efficiently, a lot more efficiently, then it becomes a feasible idea again, right? But the concept is right there. So that's why sometimes you have to read really old papers, because there are some hidden gems that maybe previously is not working, but right now it's the time to see if this idea is working again. So perceptron is actually coming from the time that when neural network is really hot. But let's see how it works. So like this one is, yeah, you can think about branch prediction as a machine learning problem, right? As we said, when you see this history pattern, what's the outcome? It's a very classic machine learning problem, as you can imagine, right? So then it's not too surprised that people would use machine learning mechanisms to predict the branch outcome. So what the idea is that they just set the inputs they just set the inputs of history as the history of your branch to be your machine learning model inputs, right? And then it could be, you can use either local history or global history, depends on your personal preference, or depends on what your design space exploration. And then gradually the hardware will train some of the, if you think about the fundamental of neural networks, it's basically a set of linear algebra functions with different weights, right? So they can dynamically adjust the weights when you are running this branch. So the idea is that we calculate the linear algebra outcome of this global history, and each bit of the history can have different weights, and see if the outcome is taken or not taken. So that's the idea of it. So graphically representation, you guys love this, I know, right? So you can consider x 0 to xn as the bits in your history, right? And each history has its own different weights, and the combination of this vector inner product will be your branch outcome, prediction outcome. And then there is an art how to adjust this branch, this weights, right? How to train this weights, which you should be able to learn. And right. So that's the basic idea of perceptron predictor. All right. So with this, right? Okay, and here's the training algorithm, right? So you can see that the training algorithm in the past is really simple because if you want the hardware to train, then that's you can only use a very simple algorithm. But as you can tell, is that if the branch outcome is true when you append this history, it looks like you are going to increment your weight. Otherwise, you are going to make it less complex. So it's actually a method trying to give confidence to which branch. So for the case that we previously mentioned that you have the randomness, this one, right? You have the randomness here. If you run this algorithm, you will figure out that if this one is not super related to your outcome, then this one could be, its weight could be evaluated at some point that we will not consider the outcome of this branch for our prediction, right? So that's another thing that the perceptron can really do. But the conventional one couldn't, because the conventional one always assumes every branch has the same weight, right? So here is the idea of perceptron prediction hardware is that you still, instead of right now, you still have the history PC, the global history. But in addition to the global history, you also have a set of weights, which is corresponding to each bit of your global history. So what would happen is that when you have a branch, you use the history to predict, and then you use the select weight vector to calculate your outcome, and that's how you get your prediction. So this is perceptron. All right. So now I thought you must read a paper. If you haven't read a paper, try to find the result right now, and let me know what's the pros and cons of each predictor. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look at what you guys feel. Well, it's definitely a question in discussion, but because we are running out of time, so what I will do is that I will just show you that. So the answer is surprisingly bimodal. So how do I know this? Actually, I don't know this. It's by the experiments from the perceptron paper, right? So if you can dig out one of the resulting graphs here, here is the percentage of misprediction. And when you have really limited hardware budget, as I said, 1 kilobyte, all predictors are doing terrible. However, surprisingly, the bimodal is doing a good job. So one of the explanation is this, right? So for the perceptron or the global predictor, you really need, or LTAGE, whatever, right? You really need a lot of history, a lot of time to train, which your hardware resource may not allow you to do so. Right? So when the hardware is limited, maybe a simpler approach is good. So that's why perceptron, this idea is really good. However, it didn't lie in the past because it needs a lot of hardware to do it, to make it happen, to make it efficient. Right. So that's why previously we don't see a lot of perceptron a predictor implemented. But right now, with hardware technology, allowing us to put more circuits within the same area with reasonable cost. New processors like AMD Ryzen processor, like Samsung mobile phone processor, they all use perceptron-based branch predictor. So this predictor is actually now living in your computers. If you are using an Android phone or if you are using an AMD-based machine, they are using perceptron. Okay. And there are other examples here, like tournament predictor has been used before in digital alpha, which I believe its grandfather almost of you probably know that is, and AMD Osmo processor, and global branch predictor is simple, but even until core 2 processor, they are still using it. And the local 4-bit and history, global history for and local 4-bit one is actually using an early generations of the processor. So every branch predictor we introduce here are actually being used in somewhere, right? So that's actually interesting that we can see here. So now I'm going to moving toward a topic that is more interested from my end, and I'm encouraging you to brainstorm with me on this one. So, I know you guys like big code, right? So that's why I'm trying to format the question of pop count like this. So pop count is a question that I give you a number, how many bits of them are ones within the number of ones, and it has a lot of applications. So that's reformatted in big code format, right? So it's actually given a 64-bit integer number, find the number of ones in the binary representation. Example 1, input 9487, output 7, because if you translate the binary representation of 9487, it actually contains 7 ones in here, right? So that's the question, right? And you can think what you will do is that you will have a program which implements the pop count function, right? Now, I have 4 different implementations. Which one do you think will be the best? Wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see what you guys think. Okay. This is a very interesting distribution. So, can I have some of you share your insights with me?
We want to choose the option of the least branches.
Okay, you want to choose the option with the least branches.
Yes.
But how do you know the fourth one has the least branch?
Oh, no, well, it's easy to predict, though.
It's easy to predict. What else? Okay, let's run the code, right? And I guess you probably think, huh, what looks abnormal is probably the one that's the right answer. So, well, yeah, so for the version A, as you can see, it already, well, I have a previous run here, right? It takes about 30 seconds. Right.
Wait, why did you run it again then?
Why? Because I just want to show you that I'm lying. Right, so it takes 30 seconds, as you can predict it. 30 seconds is a long time. And I can use this time to drink more water, I guess. Okay, 30 seconds. Okay, now the version B. Version B. Version B. Version B. Still takes a while, right? Still takes a while. But is it getting better? Okay, slightly better than A, right? 5 seconds better than A. In terms of a computer architecture, that's already a big move. So how about version C? Okay, wow, a lot faster. Only 7 seconds, right? So how about version D?
Oh, wow.
Wow, it's just 5.5 seconds, right? So what was the magic behind each pieces of a code, right? Look at this, right? The first one is the most simple and naive, right? And most, as you can imagine, well, as your experience from these classes, you already know that's probably not the answer that I'm looking for, right? But for B, it looks pretty ugly, but it at least better than A, right? Now, the code of C looks better than B, right? How come? And now, D is even better than C. Why is that? So that's actually something that we will talk about in the next lecture. In the meantime, I think it's also something that we can talk about, right? So you guys remember this demo, right? So can some of you give me a summary? Given you learned branch prediction, why adding a sort making the performance a lot? Yes. Right, so here's the thing, right? So for this branch, if your data is not sorted, it's actually judging on random data. But when you have your data sorted, after a certain threshold, your branch prediction will be always correct, no matter which type of predictor you are using. Right? So that's why sorting is such an important algorithm. Because in a lot of cases where we need branches to judge what's the condition, if you have your data sorted, and most of the time, we know for sure, well, most of the time, people tend to traverse data in an order. Right? If you can sort your data in an order, it would actually make the branch a lot easier to predict, which makes your performance better. All right? So before you leave the classroom, there are a few things that I still want you to know. Okay, here. So we have assignment 3 due next Monday. I will release the assignment later today. There's another reading quiz due this Wednesday about dynamic instruction scheduling, which I will also release the quiz as soon as I could. And again, project is released, and here is the grading rubric. So first of all, there is a 20% report. Make it short, so that it's easier for me to read it.
What's like the bare minimum for full credit?
1 page.
Like double space?
Okay, so here's the element. Tell me what metric you use for your branch prefetcher. Okay, so think about this. What you really need to give me is you have to run a few traces, right? We mentioned that. You have to run a few traces and you have to tell us your result, your performance using that traces, and you have to tell us what kind of magic you implemented in your prefetcher to achieve that performance. And probably a few sentences that, okay, it's a competition, right? Which can help me that if you won the prize, what should I describe your predictor, the prefetcher? Okay, so those are the elements that I think are very good to include. So 20% of the report. If your code can compile and run 20%, and surprisingly, there are always cases that people fail to get this 20%. So make sure that you test your code on the machine that.
Are you going to be compiling it on a Mac or?
No, I mean, we
that?
check the GitHub. We set which machine we are going to set.
Oh, okay.
Right. And finally, 60% performance space. The sample prefetcher is the baseline, and your score will be using minimum speed of -1. And so if you can speed up by 2, you will get full scores in this part. If you didn't get any speed up, you may have negative score for this part.
What?
Yeah. Well, I gave you the sample predictor,
Oh.
right? So if you do nothing, just turn in the sample predictor, right? You can at least get 40%.
80%.
That's what I said, right? But if you do something negative, it would actually make your grade lower. Okay. But if you try to do something better, right, you can at least get 41, 42, something like that. Fair? All right. So work on that. The due date is November 29th, which is pretty close. Other than that, enjoy the rest of the day. I will see you later.
Yeah.